Okay, in this chapter we talk about the two-dimensional problem in polar coordinates. We first consider the equilibrium equation in polar coordinate. See, in polar coordinate, the material point is look like this. It is not a rectangle again. In rectangular coordinate, you will have a rectangle shape of material point. But now, this is the material point in the polar coordinate. See, this line and this line are two radius, and this line and this line are two circular arc. Okay. So along these lines, we have some stress component. This is the sigma R, means that the normal stress in the R direction. This is the shear stress component in the theta direction. This is in the top. We say that it's in top. And here, this is the normal and shear stress in the downside. Okay, and in the same deal, we have the normal stress and shear stress in the left side and right side. Okay. Now let me consider the equilibrium relation in the R direction. Okay. Of course, we will have another direction, another equilibrium relation in theta direction, but we just consider the R direction first. See, there is a tricky point. As a material line, a material coordinate, you can say that we have a radius here, we have a radius here, we have radius here. We have a lot of radius inside the material point. So which radius should be the one we choose? This is easy. We choose the middle one, right? So the radius in the middle plane is the radius we consider. So the definition of R direction is defined according to this radius. Understand? Not this radius. Okay, not this radius, but this radius. Okay, and also the theta direction is defined according to this line. Okay, perpendicular to the radius here. Okay, this is a tricky point. Why? Sigma theta acting on the right side, okay, on the right side, is not perpendicular to this one. See, this is the sigma theta. It is perpendicular to the right side of the material point, right? This is the right angle here, okay, 90 degree right angle here. But this sigma theta, this stress component point, is not perpendicular to this radius. So it is perpendicular to this radius, but this radius cannot represent the R direction. So what will be the result? The result is that the normal stress here, sigma theta, have some component, okay, has some component in the R direction defined here. Means that you have a sigma theta, a vector, you extend it to here, and then you will find that this vector is not perpendicular to the radius here. So since it is not perpendicular to the radius here, you should have a component in the R direction and component in the theta direction. Understand? So this situation enforce us to consider the projection of this vector in the R direction and theta direction. Okay, let us do it. Consider the angle here as the theta, and half of the angle is we cut the material line by this radius, so it is half of the theta. It is obvious, okay, by definition. Okay, and then according to this picture, we can draw a parallel line, okay? This line and these lines are parallel to each other. We draw a parallel line here. So this phi can move, this angle phi can move to here. Okay, since this is angle phi, so it is easy to figure out that this angle equal to this angle, and this angle equal to this angle. Okay, so now according to this rectangle, little rectangle, we can find out the components in the theta direction. This is the theta direction, this one. Why? Because this direction is perpendicular to this r direction, right? So this is the theta direction. Okay, so we want to compute the component of this vector in here. So we project this vector in this direction. So we multiply this vector by cosine phi. In the same way, if we want to compute the component, this vector, the component in the r direction is this one. We should multiply the sigma theta dr by sine phi, means that this one is sine phi. This is phi, so this is sine phi. Just this one equal to this one. Why we have a dr here? It's simple because sigma theta itself is not a vector. It is a stress. But when it is multiplied by dr, it becomes a force. Okay, so it is a force vector. So in this way, we can decompose the force vector in the theta direction and r direction. Understand? Once you have done this, you can consider the equilibrium relation without trouble. Okay, but before we do this, we also emphasize that the line here is dr. Okay, and the arc length here for this one is this one. What will be the length? The length is here. This is r. Okay, this r, and this is dr. So this is dr, and so this is the d theta. D theta. Okay, so the arc length here is r past dr times d theta. This is the arc length, means that this is the r past dr d theta. Okay, and in the same way, the arc length here is what? R times d theta. Okay, like this. Okay. If you understand this, now we can consider the equilibrium relation. See, we have this one, the equilibrium relation in the r direction. First, we consider this component, this one, sigma rr at the top, times the multiplied by the what? By the arc length here, the arc length. Okay, we had illustrated before. And then also this component minus this component, times the arc length. Okay. Besides of these two components, we have sigma theta, as we have mentioned before. Sigma theta has a component in the r direction too. This one, right? So we consider it here. It is pointing downward, so we have a minus sign. Okay. In the same way, this is right side. How about left side? Left side also have sigma theta. Okay. So it also have a component in the r direction like this, as just in the same way as this one. So this one come from here, and this one come from here. Okay. Besides of the normal stress in the theta direction, we have the shear stress in the r direction too, right? So this is a shear stress, and this one can also be decomposed into the component in r direction and theta direction. And the formula is easy, since sigma r theta is perpendicular to sigma theta, right? So the component of sigma theta in r direction is written by multiplied by sine phi. So sigma r theta, if you consider the component in the r direction, you should multiply it by cosine phi. The reason is simple, okay? So this one can be written here, and no, this one, okay, this one can be written here, and times cosine phi. I make some mistake here. This one is pointing downward, okay? Pointing downward should have a minus sign. So I make some mistake to write it as left. It's wrong. Change it to right. Change it to right, okay? Means this one, okay? It's pointing downward, okay? And also we have another shear stress in the right side, okay? This one, in the left side. This is r theta in the left side. Okay, this one, and it is pointing upwards, so this is path sign. So you should change right to left. Okay, erase this LEFT. Okay, erase this RIGHT, and then we are done. Having this equation, we copied to the next copy this equation to the next page. Here. Okay, we just copy the same equation here. Now we can divide this equation by dr d theta at the right left hand side and right hand side. It doesn't change the equality, and this one equal to 0, and this one will cancel out with this d theta. Will cancel out with d theta, and then we have this one like this, and dr written like here, and when we consider this term, these two quantities will be cancelled out. So we have this one, and this one have become here, and this one become here. Okay, and as we have mentioned, okay. Again, you should change right to left, left to right, right to left. Erase it, change it LEFT. This erase it, change the RIGHT, okay? And then according to the illustration before, this is the differentiation of sigma r with respect to r. And this is the differentiation of sigma r theta with respect to theta, okay? And this one will equal to this because the material point is very small. When taking the limit, when we take the limit, this term will be just equal to this term. And also in the same way, because the material point is very small, these two terms, the average of these two terms is equal to sigma, theta. Okay, so finally we end up with this equation now by consider the equilibrium state in the r direction. In the same way, you can consider you can have the equilibrium equation in the theta direction. I won't do it here. You can do it by yourself. Okay, as before, if you have a set of equilibrium equation, you may define the stress function, right? Area stress function. But now these two equations are written in terms of the polar coordinate. So the stress function will be a little bit different from those before. Okay, and I write it down right here. Phi is the stress function. By differentiating the stress function, you can get the stress component. Okay, I won't present the detail here. You can figure it out by yourself. And also, there is a relation between the stress component in the rectangular coordinate with those in the polar coordinate. Okay, this is called the Mohr circle. You can find it in the undergraduate textbook. So I just copy it down here. Here, S square equal to S theta square. It is the abbreviation. C square means that it is a C cosine theta square. It is abbreviation. And these two is just like this, written like this. And also we can express the stress component in the rectangular coordinate in terms of the stress component in the polar coordinate in the same way. Finally, we can also express our biharmonic equation in the rectangular coordinate, xy coordinate, change it to the expression in terms of the polar coordinate. The details of this transformation is quite tedious since we are interested in solving the solution. So we won't go through the detail to derive such kind of transformation. If you are interested in the calculation, you can do it by yourself.